Okay, so I think we will start. Thanks for coming for the last tutorial session. By the way, don't forget we will have a surgery hour, so similar as the one before coursework. We'll have another on, I think, should be on 13th of December, so the usually Monday lecture session. So 3 GTA and Ben will be in the Reynolds, so that big lecture room, lecture theater, and answer your questions there. So if you need any help, you have any questions regarding to coursework, exam, lecture notes, whatever, feel free to come and we can have some discussion. All right, I think Ben will announce this next week as well. So yeah, just let you know. Okay, so there will be 8 questions for today's tutorial. Since the fourth one has been, well, a similar one has been covered by Ben during his lecture, so I will put that in the end if we have time, and I will go over the others. Okay. So the first one, we have a Venturi section. And in the, so we have D1 in the middle and D2 at the outlet. So it connects with a tube into a reservoir. So I use another color. And it is used to draw the fluid upward from a reservoir. So we assume the water are all in the pipe. So the pipe height between the Venturi section and the liquid and the reservoir water level is h. So we have D1, D2, and h, and also, well, there are something not clearly explained. But for this tutorial sheet, there are some so something's not clearly described in the problem in the questions. But usually you can kind of know, kind of feel what you are required to, what you need, what parameter, what variable you need to solve the question. So it kind of encourages you to do the assumptions on your own. Okay. So we also know PA, and here one thing was not mentioned in the problem is we need to assume same liquid in Venturi section and reservoir. Okay, so then we can solve the problem. So from the problem, the first thing we need to think about is it says explicitly use Bernoulli equation to do the things. So we need to first check if we can use Bernoulli in this scenario. So first, this one is steady, it's incompressible, and is inviscid. So we can use Bernoulli. We can use Bernoulli's equation. All right. So, and then we need to consider. So we first consider this point, or maybe it's red. So this point. You can all see this point clearly, right? So for this point, what we have is a point on the tube right at the water level. Okay. So for this point, we assume the pressure in the Venturi tube is P1 in the middle, and at the outlet is P2. So this gives us P1 plus, for this height is h, so rho times density times gravity times h should be the same as the pressure at this point. So pressure at this point is PA. So we first have this equation. And then we apply the Bernoulli equation for this Venturi tube, since we do not need to consider about the gravity effect. So P1 plus half rho V1 squared should be the same as P2 plus half rho V2 squared. Right, so we know P2 is PA, and what we want to know here is we want to know the outlet velocity. Right, and also another thing we know here is we know the continuity equation. So for the continuity equation, we have V1 times A1 should be the same as V2 times A2, since the flow is incompressible, right? So this gives us V1 times pi times half D1 square should be the same as V2 times pi times half D2 square. So then this gives us V1 should be, we have pi cancelled, 2 cancelled. So it will be D2 over D1 square times V2. Right, so we have these three equations. We have this one, we have this one, and we have this one. Okay, so we first, let's name it equation 1, 2, 3. All right, so we put 3 to 2. So this gives us P1 plus, so V1 is this one. So we replace the V1 in equation 2. That gives us half rho times D2 over D1 divided by 4 times V2 square equals to PA plus half rho V2 square. Also from the equation 1, we know that P1, so we have a relationship between P1 and PA. So P1 equals to PA minus rho GH. So we replace that as well. So we replace this as PA minus rho GH. And then we have PA cancelled. So this gives us half rho D2 over D1 divided by 4 minus 1 times V2 square equals to rho GH. So we can cancel the rho and put the 2 in the other side. So this gives us V2 equals to square root of 2GH divided by D2 over D1 to the power 4 minus 1. So this is our final result. Any question about this one? Yes, please.
So we use Bernoulli equation. We assume that the fluid in the reservoir and the fluid in the venturi are exactly the same thing. So, and we put P1 is equal to PA plus rho GH, and P2 is equal to, as in the static pressures.
Exactly.
P1 is equal to PA plus rho GA, and P2 is equal to PA plus.
P2 is equal to PA.
Okay, so we take P1 and P2, insert them into the Bernoulli equation.
Yeah.
Assume that all densities are the same thing, and use the V1A1 equation, and that's it.
Yeah. So is there any question?
No.
Okay. Yeah. So here you are asked to use almost all the things you have learned in this module. So this is kind of a good question, but the scenario here is a little bit suspicious. So the question described as to draw fluid upwards from the reservoir. So apparently the flow doesn't go into the venturi section. Otherwise, if it goes to venturi section, you can no longer use Bernoulli because you change the you change the mass flow by input as something else. So it says draw the fluid upwards but not into the reservoir. Also, it also double check this by saying which is just sufficient to cause the reservoir fluid to rise in the tube up to section 1. So then you don't need to worry about so you can still apply the continuity equation in this problem. Yeah, this is a bit confusing, but yeah, so maybe it's better to say something about the exam. So in the exam, you will face problems similar as your coursework. So they won't like tutorial, they won't give you a question directly and ask you to solve it from nothing. It will let you to solve problem step by step. So they will give you hints in the middle. And usually, I think from experience from last year, so you will have 100 total marks for the final exam and 2 hours to 120 minutes. So usually, you should wisely spend your time on each problem. So don't stuck yourself in one specific problem too long. So for example, you usually won't want to spend 2 times of the points. So for example, if a question was 5 marks, you usually won't spend more than 10 minutes on that. Otherwise, you won't have enough time to do the rest. Okay, this is a kind of general experience. And yeah. And also, well, nobody can review the things. Usually, nobody can have a very good review on every section. So when you get your problem sheet, you will probably first look at which question is regarding to which part of the problem. So for example, this one is for Bernoulli, that one is for pressure, that one is for drag, or that one is for energy equation, so on and so forth. And that one is for head loss, say it like this. So maybe you are good at head loss, so then you'd better solve the head loss first. So make sure you get the maximum points or maximum marks you can during the exam. All right. Yeah, so let's continue let's go to the second one. So question 2, in figure 2, we have a fluid in air. So it's kind of compressor. So we have a tube. Something like this. So we have D1 equals to 0.1 meter, D2 equals to 0.1 meter, 0.06 meter. And for the fluid, we have the distance, the height difference as 0.08 meter. All right, so here the specific gravity is 0.827, and the density of air is 1.2 kilogram per cubic meter. Okay, so we assume no viscous losses. So that's basically hints you can use Bernoulli. We have steady, we have incompressible, we have inviscid. So we can apply Bernoulli here. So it asks to calculate the volume flow rate Q in cubic meter per second. So it also lets you into cubic meter per second. All right, so here we have a very typical manometer, but when we apply manometer, we need to first identify which pressure it measures. So for example, for this bit, for the tube at 0.1, so we have 0.1 and 0.2. So for the pressure at 0.1, since it's in the same direction as flow, so it measures total pressure. So this means we have P1 plus P, so we have, well, P static at 1 plus P dynamic at 1. So this gives us P1 plus half rho V1 squared. But for P2, it's slightly different. So for P2, so for 0.2, since this one is perpendicular, it's normal to the flow direction, so we only have P2 here. So this is P static pressure. So we measure static pressure here. So this equals to P2. All right, so here we have a height difference. So this indicates the pressure difference from this end to this end, from 2 ends of the manometer. So this gives us P1 plus half rho V1 square minus P2 should be equal to rho G delta H. All right, and then we can, so if we look at this, we don't know, what we know is we know the rho G delta H, yeah, and we don't know anything else. But also, don't forget we have the diameter of 0.1 and 0.2, so this indicates we can use the continuity equation. Right, so by using continuity equation, we have A1 times V1 equals to A2 times V2. So this gives us half D1 square times pi times V1 equals to half D2 square times pi times V2. All right, so then what we get here is we cancel the two. So we know again V1 equals to D2 over D1 square times V2. So then finally what we want is we want Q equals to A2 times V2. Right. So then now what we are going to, so we have density known, we have gravity known, we have delta H known, and yeah, so finally we need to apply the Bernoulli equation. So for Bernoulli, what we have is we have half, so P1 plus half rho V1 square equals to P2 plus half rho V2 square. Right, since we don't have the gravity effect in this problem. Okay, so then we know that half rho V2 square equals to P1 plus half rho V1 square minus P2. So this gives, so this is the rho G delta H. All right, so we have density cancelled. No, sorry, it's not density not cancelled. My problem. So here the density is air, and here the density is the manometer fluid, the marine oil. So we have rho A and rho M. But since for this one we have it as rho water times specific gravity, the air density is also known, so we can easily find the V2. Yeah, so the V2 square is 32.9 meter square per second. Oh, sorry. The V2 is 32.9 meters per second, and then we have the Q equals to A2 times V2 equals to 0.093 kilometer per second. Yeah, so that's for problem 2. Well, wait, so generally we don't need to apply continuity equation in this problem. Sorry, this is my fault. Yeah, so, yeah, please.
So basically we use this equation, we separate out half rho V2 squared into a separate place whose rho is the rho of air.
Yeah.
And that is equal to the rho GH of the Mirian oil.
Yeah, because
which is equal to the change in pressures between P1 total and P2 static.
exactly.
Wait, but how do we get to P2 static?
Because if you look at the manometer, the tube's position is normal to the wall of the venturi channel, right?
So that's how P2 tubes work. They only use the static air.
Well, P total, so P total tube is a measurement of P total. So that is when the tube is normal, is parallel to the flow direction. So if you look at these, if you have your problem sheet, so look at the figure. At the inlet, the tube direction is the same direction as the flow direction. So that is the measurement of total pressure. But for the other side, for the point 2, the tube direction is normal to the flow direction. So that is the static pressure. So when the tube direction is normal to the flow direction, that means you never consider the dynamic part. You never consider the velocity part.
So this is a pitot tube where the static pressure, where the stagnation pressure is the pressure at the end of the beginning of the pitot tube.
Yeah. So.
And the manometer over here at point 2 is a pressure tapping.
Yeah, exactly.
Thank you very much.
Everyone understand? Everyone understand this one? Yeah, cool. Yeah, so this is a little bit tricky. You need to first identify which pressure it measures, and then you can do the calculation. Okay, so let's go to question 3. Well, this is another tricky one. So we have a reservoir, and for the water, we have a tube on the outside. Yeah, and it asks about, so we have the height. Oops. This is 0.3, this is 0.1, this is 0.2. Height, we have a L, and we have a small h. Yeah, is that clear? Okay. So it asks to calculate first it asks to calculate the Vx, and then it asks to calculate the pressure at the highest point of siphon. So that means we have P at y max. Right. So we define this point. Oops, y. Sorry. We define this as y. Okay. So we first look at how to calculate the Vx. Well, so here we can still kind of apply the Bernoulli, since we have, it's not fully steady, but if we think the height of the water in the reservoir decreases in a constant and in a not very rapid, so we can still treat it as a steady case, and also it's water, so it's incompressible, and also we assume it's inviscid, so since there are no viscous losses, so we can use Bernoulli in this problem. Okay, so we first consider from point 1 to point 2 what we have. We have applied the hydrostatic pressure, or it's the same kind of as Bernoulli if you consider the gravity effect. Okay, so for P1 plus density times G times H should be equal to pressure 2. And then from 2 to 3, what we have is we have P2 plus half rho V2. So here we apply Bernoulli equation. Use Bernoulli's equation. So we have plus rho G Z Y2 equals to P3 plus half rho V3 square plus rho G Y3. Okay, so we put Y2 to the other side, so this gives us rho g times y3 minus y2. So we consider the distance between these two. So this will be h minus big H minus small h. Right, so this will be rho g times minus h. Don't forget here we have a minus sign because the 3.3 is in a lower position. All right, so then we can see what we know from the from these two equations. So we first know that P1 is atmosphere pressure. Oh, let me use it another color. Oops. So this is atmosphere pressure, and also the same as P3 is atmosphere pressure again. And also we know velocity at point 2 is 0, so we have 0 here, and this is Vx squared. All right, so we also can replace P2 by PA plus rho gh. So then we have the expression in the form of PA plus rho gh plus equals to PA plus half rho Vx squared minus rho gh minus big H minus small h. PA cancelled, and we have minus, so it's a plus h, and we have a plus h here. So h cancelled. So this gives us half rho Vx squared equals to rho gh. Density cancelled to the other side, so this gives us Vx equals to a square root of 2gh. So this is the first question. For the second question, we need to apply the continuity equation. So, well, it's not applied, but we need to use the idea of continuity equation. So here it kind of suggests you that for this pipe, the diameter doesn't change. So based on the continuity equation, the velocity at point 3 must be the velocity at the top point. So then we know that from point 1 to top, what we have, or maybe from point 2 to top. From point 2 to top, what we have P2 applied Bernoulli equation. We have half rho V2 squared plus rho g y2 equals to Pt as P top plus half rho Vt squared plus rho g y top. Okay, so for this equation, we have P2 equals to PA plus rho gh. We have V2 as 0. We have, again, we put the y2 to the other side. So it gives us rho g y top minus y2. So this is L plus small h. And then we also know Vt, velocity at the top, again, as we said, according to the continuity, the velocity at the top must be the same as velocity at the exit. So this means we have Vx here. So then we have the equation as PA plus rho gh equals to Pt plus half rho Vx squared plus rho g L plus h. So again, we have h, small h cancelled. And for half rho Vx, this should be rho g big H. So then it gives us Pt equals to Pa minus rho g L plus H. So this is the final answer.
Could you go over the last three lines of how you got Vx?
So why Vt equals to Vx? Is that the question?
Yeah, but then how, I'm not sure how you got Vx equals root 2gh.
Okay, so you mean here, right?
Yeah.
So we first use P1 plus rho gh equals to P2. So this gives us P2 for this equation, for the second equation, right? So we replace P2. Also, we know that velocity at point 2 is 0. So we don't have the dynamic pressure there. And we know the height difference between point 2 and point 3. So we have y2 and y3. And we also know the P3 is the same as atmosphere pressure. So we have P3. So the only unknown in this Bernoulli equation is V3. That is Vx. So we get Vx. Is that clear? Okay, cool. Any other question? Yes, please.
Wait, so the beginning Bernoulli equation is PA plus half rho 0 squared plus rho g 0 is equal to PA plus half rho Vx squared plus rho gh. So
Not really. Sorry, what do you mean by very initial? Which 2 points are you comparing?
1 and 3 are my initial points.
Okay, so if you compare 1 and 3,
Yeah.
that will be at point 1 you have 0 velocity,
Yes.
and so that will be half. Well, I can write it quickly. So at point 1 is P1 plus half rho V1 square plus rho GY1 equals to P3 plus half rho V3 square plus rho GY3. Right, so this one is atmosphere pressure. We have 0 velocity here, and we put this in the other side. So this gives us rho GY3 minus Y1. 3 minus 1, so that is H, so rho GH. Right, so it's the same then. We have this one as PA, so PA cancelled. And here it should be minus because we use the 0.3 minus 0.1. So this is minus rho GH. So this gives us, density cancelled. So this got V3 squared equals to 2GH. It's the same.
Okay, so where did you get that minus from again?
Because we're using 0.3, Y3 minus Y1. So you use a lower position minus the upper position. So you definitely get the minus Y.
So h is less than 0.
Well, this is a height difference.
Yeah.
So you have, if you think of this in head, so you have a kind of head loss. You convert the gravity, the potential energy, to the dynamic energy.
I mean by h is less than 0, as in the point that is marked by h distance.
Well,
0 is less than that.
Well, you can say it's less than 0. It's totally up to which reference point you are choosing.
I'm choosing 0 as my reference point. At being.
Which position is 0 as your reference point? But anyway, so you can have a negative height. That's totally fine as long as you have your signs in consistent way.
Well, and I think I now realize my mistakes.
Right. Okay, it's all right. Let's go to question 5. Since 4 has been covered in your lecture, we can go through it if we have time later. All right, so it's a bit behind the schedule. Okay, let's be quicker. So we have air in 20-degree forms and boundary layer near a solid wall, and it says in a sine wave shaped velocity profile. So that means if we have velocity y, it should be a times sine omega y plus phi. So it should be in the form of this. And then it says, okay, so the boundary layer thickness, boundary thickness is 6 millimeter. So that's 6 times 10 to the power minus 3 meter. And the peak velocity, U infinity, equals to 10 meter per second. So it asks to calculate the shear stress at the wall at y equals 3 and y equals 6. All right, so for the shear stress, is the equation is pretty straightforward. It's viscosity times partial u over partial y. So here, the only thing we need to know is partial u. So how to get partial u? We need to fit the boundary layer data into our profile. All right, for this profile, there are several things we know. So first, we know that the total heightness, the height delta equals to 6 to the power minus 3 meter. So that means so U infinity should be A times sine delta times omega plus phi. And also, what we know is, if we think about the sine wave, y and u, so we only should consider this branch. So we have this period. So this means we have when for delta equals 6 minus 4, we have sine equals to half pi. So that means, so that means sigma times omega equals to half pi. So this gives us omega equals to pi over 2 times sigma. Oh, sorry, 2 times delta. And yeah, and the last thing is we can directly have A, since the maximum value, so the free stream velocity is 10 meters per second. So we have A as 10 meter per second. Also, we have the phi as 0 because there's no phase change in the equation. So this gives us the velocity of y, the velocity profile as 10 times sine pi over 2 delta times y. So this is the equation. So with this equation is pretty straightforward. Shear stress equals to partial u over partial y. Viscosity times partial u over partial y equals to viscosity times 10 times pi over 2 delta times cosine pi over 2 delta times y. All right, so this is your shear stress. And then it just asks you to calculate at different positions. So you put different y into it, and you will have your on the wall will be times 10 times pi over 2 delta equals to 0.7 Pascal. And at y equals 3, it should be the same. It's just you just put a number there. It should be 0.033 Pascal. And in the edge of the boundary layer is free stream, so the shear loss is 0. So these are the answers. So for this question, the only difficulty I think is how to find out this velocity profile. So you need to convert it to you need to convert it from this to this. Yeah.
I wanted to ask something about the very top beginning of the equation.
Yeah.
Uy is equal to a plus y sine plus, what was that letter at the end? A.
It's phi. So this is a phase change. We don't have phase change here. We don't have a phase here. So this one should be 0.
Oh, okay.
Yes, please. Sorry.
Yeah, right after calculate for the, because we're going to be plugging in for y values, right? And then I just didn't get the delta right at the end.
The delta is the boundary layer thickness.
Okay, fair enough.
Okay. Yeah. Any other question? Okay. This one is pretty straightforward. The next one is much more complicated. It's a advanced usage of what you just encountered. Okay. Question 6. So you have a fully immersed disk in oil. So basically, this is your disk, and you have oil outside, and we say outside we have a frame. So the disk is rotating. We have a radius r, and we have a angular velocity omega, and the viscosity is mu. So when the disk is rotating, remember we have the non-slip wall. So we definitely have a velocity profile like this. Let's say this is the center line, and we have, okay, so for this point, say, we have a distance of small r. So this value should be r times omega, and this value is 0. This step is clear. Right, so the disk is rotating. We have on the disk for an arbitrary point with a distance r from that point to the axis. We have the linear velocity on that point as r times omega, and then it can form a boundary layer as a problem described a linear velocity profile. So that means we have a linear shape here. Is that clear? Yeah, cool. So then, since it asks to derive expression about viscous torque on the disk, so the torque should be the force times distance, right? Force times length, and the force should be the stress times area. So what we want to really know is this stress, is the shear stress. So how to calculate the shear stress, again, as we said, is viscosity times partial u over partial y. So here we have the linear relationship for an arbitrary r, for any r. For any r, we have the velocity profile as u equals to, remember we have omega times r here, and we have 0 here. The total distance, we call it h. Yeah, this one is something not given in the problem. You need to assume it yourself. So we assume the distance between the disk and the boundary as h. That clearance noted in your question sheet. That clearance should be h. So for this h, we have we can have the slope. The slope will be omega times r divided by h times y. So this is your velocity profile at any r. Okay, so then you can have your torque. You can have a shear stress at any r as partial viscosity times partial u over partial y. So that will be mu times omega times r over h times, yeah. So that would be this one. Okay, so then for each point, since we have torque here, we have shear stress here, we can, for any r, we can have the force on that small as torque times dA. So we consider it as a small element over the disk. So for that small element, we can have a friction force calculated based on the shear stress times the area of that small element. Right, so that is dF equals to tau times dA. So this dA, we can think as d times pi r square. So this gives us 2 pi r times dr. So this gives us dF equals to mu times omega times r over h times 2 pi r dr. So then, still remember for this bit, we have the force, we need to calculate the torque. So we have the torque as dF times r. So this gives us r times omega r over h times 2 pi r dr. So then we need to do the integration, since we know the torque on each small element on that disk. So we do the integration. Don't forget we have two sides, so torque will be 2 times integration of the disk area dt. So that will be 2 times 0 to r times of r times mu times omega r over h times 2 pi r dr. So it's r from 0 to the whole radius. So this will give you pi mu times omega r to the 4 over h. So this is our final answer. Yeah, here, this question is not so well defined, so you need to assume this clearance as h. This should be given in the problem, but didn't. Anyway, yeah, so this is basically how to deal with this problem. Any question? You go first. Okay, you go first, please. Sorry.
Will this be submitted on? Will this be published on Blackboard?
Yes, it will.
Oh, thank you.
Can you evaluate like f as like an indefinite integral first, then after you substitute in to the viscous top, so like you integrate like the expression for f?
So you mean why I don't integral at df first and then do the...
You integrate it to find like an indefinite integral, then you substitute into your viscous top equation.
Sorry, I didn't understand. Can you repeat it?
So basically you find like an indefinite integral of f, then you use the expression, you substitute into your viscous top, so like t equals to the integral of f with respect to r.
Well, the problem for that is for each torque, the arm also changes with the location. So you need to put that r in the integration. So because for each small element, if the location of that small element changes, the arm also changes. Right? So you cannot put that r outside. You must have that r included in your integration. Think about if you say, for example, if we do say for d, say we have t, is this what you mean by torque df times r? That's
No, like an integral of f with respect to r, so it's like f dr.
so integral of f times dr. Yes, I think you can do that, but you didn't get the.
I think got the answer. I just want to check if it's correct.
Yeah, definitely it's correct.
So like it's like conceptually, like concept-wise, it's still correct. Just that.
No, wait a second. No, this one. So for f, you integrate it. So let me think about. No, because this. So f is not constant along the radius.
Yeah, but no, because like when you find f with respect to
So did this step. So you have df equals to 2 pi r dr.
I have F equals to the integral of shear stress with respect to
Yes. Okay. Yeah, I think so. Yeah, I think you can do that. Since you first have an expression of f based on r. So then you do the integral. Yes, you can do that. Yeah, that's correct. Yeah, any other question? No. Okay. Yeah, so cool. That's question 6. And then we have question 7. Okay, 10 minutes to go. Yeah, so we have a sphere attached to a string. So if we have the free body diagram, we have gravity, we have a drag, and we have tension from string. So the angle between the wall and the string is theta. So yeah, we define our coordinate system as x and y. So in x direction, we have since it's in a steady state, so we can have all forces balanced. So that means we have t times cosine theta equals to d, and in y direction we have t times sine theta equals to g if to gravity. So equation 1, equation 2. So we have 2 over 1. This gives us tangent theta equals to gravity divided by a drag. All right, so then the problem is how to calculate gravity and drag. This is pretty straightforward since what we know here, we know the density, the first density, we know is diameter, we know the drag coefficient, and we know the velocity and density of the air. Right, so first for the gravity is, so we have density times the volume of it will be pi times 4/3 times half d cubed times g. Right, and then for the drag, since we all know from basics, drag coefficient equals to drag divided by half rho v squared times area. So this gives us drag equals to drag coefficient times half rho u squared times pi half d squared. Okay, so this gives us tangent theta equals to g divided by d equals to density times pi times 4/3 times cube d over a times g divided by drag coefficient times half rho v squared times pi times d squared over 4. Right, so we have 8, and so we have those cancelled, we have pi cancelled, and finally gives cd times rho times u squared times, we have d squared. Okay, so divide density of sphere times 4/3 times d times g. So don't forget, we asked the problem asks us to calculate theta, so we need to get theta as arctangent of 4 times rho dg over 3 times cd rho v squared. V squared. Yeah, so first we got the theta, calculate the theta, and then it asks us to put numbers in. So all the numbers are given. We have density, of the sphere, we have density of air, we have d, we have cd, we have velocity, and we also know the gravity. So everything is known. So we have theta equals to 79.9. So this is our final answer. This one is pretty straightforward. Is there any question? Yes, please. This bit? Yeah, well, this one will be